Today we are going to do differentiation 2. So at this stage, we assume you would have covered the first part of differentiation. So for your differentiation 2, we start off with the exponential form of differentiation. All right. So for your exponential form of differentiation, this is what happens. The derivative of e to the power of ax plus b is equal to, so what do you do here? You differentiate the power here when you want to differentiate e. So if you differentiate the power, it's going to give us an a. And then what you do, you then rewrite your e to the ax plus b as it is. Then the next form of differentiation that you are going to do is the logarithms. So for your logarithms in differentiation, we are saying derivative of the natural logarithm of a certain function. It could be linear, it could be anything else. How do you differentiate this? So what you do is you look at what's in front of your logarithm right here. You differentiate that. So in this case, it's going to give us an a. And then what do you do next? You then replace back your ax plus b in the denominator. So we're just saying it's derivative of what's in front of the logarithm. You put it as the numerator over what's in front of the logarithm. All right, then we move to the next type of differentiation that we should cover. It's in the form of trigonometric functions. So trigonometric differentiation, what are we going to do? We have the following basics. We have derivative of sine x being equal to cos x. We also have the derivative of cos x being equal to negative sine x. Then we also have the derivative of tan x being equal to sec squared x. So these are the basic trigonometric differentiation that we have. Then still on trigonometric differentiation, we should also be able to do some composite angles in front of these trigonometric functions. So by that exactly we are saying, if we are having the derivative of sine of a composite angle like this one, or a sum angle, which is sine of let's say ax plus b, like this. So how are we going to differentiate this one? Well, we start off by differentiating the composite angle right there, which is the ax plus b. If we differentiate that, it's going to give us an a, and then that multiplies with your derivative of the derivative of the sine function. So derivative of the sine function is going to give us a cosine. Then of course, what happens thereafter? You retain your angle as it is. So once again, I'll take that. You differentiate the angle, right? You differentiate your angle ax plus b, and that's going to give us an A. And then you differentiate your sine function and it will give you a cosine. Then of course you retain the angle as it is, AX plus B. All right, so moving on, we are also going to differentiate the cosine of AX plus B. So once again, you start off by differentiating the angle, which is our AX plus B. And when we differentiate that, that's going to give us an A. Then multiplied by the derivative of cosine. So the derivative of cosine is a negative sign. It's a negative sign, and the negative sign is multiplying with A right here, and it would give us negative A sine, and we bring back our angle as it was. Okay, then from here, we are also going to do the derivative of the tangent of a composite angle AX plus B. So once again, what are we going to do? We are going to differentiate the angle first. So if we differentiate the angle, that's going to give us an A. And then we differentiate the tan function. And if we differentiate the tan function, that's going to give us sec squared. And of course, our angle, as usual, comes back as it is. Okay, what else are we required to understand before we start this differentiation 2? We are supposed to understand the differentiation of products. The differentiation of products, we have two items that are multiplying each other, and we want to differentiate them. So if you want to differentiate a product of two items that we are going to call U and V, if you are to differentiate a product of U and V, this is going to be U times the derivative of V plus V times the derivative of U. So that's how we deal with products. And then what's next? Now we are going to deal with quotients. How do we differentiate quotients? So by quotients, we are talking of fractions. We want to differentiate a fraction of variables U and V. So how do we do that? V times the derivative of numerator U, subtract U times the derivative of denominator V, all over what? All over the denominator squared. So V du minus U dV over V squared. That's how we differentiate our quotients. And then moving on, we are also going to do some parametric differentiation. So we need to understand how parametric functions are like. So parametric functions, we are saying we have x being equal to a function of a certain parameter t. I'll take that again. Right, we have x, which is expressed as a function of a parameter t. We also have y, which is also expressed as a function of the same parameter t. So now we want to find dy dx, the derivative of y with respect to x. So now what we are going to do is, firstly, you get your dx dt. Okay, so our dx dt, let's just assume it's given as a value of a. Then we also get our dy dt. Let's assume this is given as a b. So to get our dy dx, we then connect these two rates. We're going to connect the dx dt to the dy dt. We're going to connect these two. So let us connect them through connected rates of change. This is going to become dy dt multiplied by dt dx. Yes, it has to be dy dt multiplied by dt dx because the dt and the dt, they can cancel out each other. And of course, we then remain with dy dx. So that's what we want to do. So then what are we going to do next? We then say dy dx is equal to dy dt. We had assigned a value for dy dt to be equal to b multiplied by dt dx. So when we talk of dt dx right there, it's a bit of a contrast to dx dt because dx dt is equal to a, but this one now that we are talking about is dt dx, which is the inverted form of that. So we'll bring that as 1 over a. So that's how we find our dy dx for the parametric functions. Right, moving on, our syllabus also requires us to understand the implicit differentiation. So for your implicit differentiation, what are you going to do? We are going to say this is basically the derivative of y terms. Yes, we can think of it as the derivative of y terms. So when you differentiate a y term in whatever form that it is, you want that in terms of x, or with respect to x rather. What you do is you just do your differentiation using the same old methods that you were just applying for x. So like in this case, power times coefficient, that will be k times n. Then you subtract 1 from the power. Right, you have differentiated just like you do for all the other terms in x, as previously discussed in differentiation 1, and of course within this video in the past 18 minutes. You just apply the same principles for x. But most importantly, I had to use a different color for this one. You then put a suffix of dy dx. So whenever you are differentiating a y term, you just do the same thing you were doing for your x, but you should always put the suffix dy dx. So that's with implicit functions. Okay, so moving on, we are also going to talk about tangents as well. Tangents, we had them in differentiation 1. We are still going to have them in differentiation 2. So we are going to define tangents. For those who don't know what a tangent is, we are saying we have a curve, right? That's a curve. Then what's a tangent then? A tangent is going to be a line that touches the curve. This one is refusing to touch. It's cutting through. Let me take that once again. It's a line that touches the curve. Yes, perfect. So as you can see, it's touching this curve. It's not cutting right through. It's just touching the curve at a single point. That's a tangent. So now that we have defined what a tangent is, it being a straight line, this means your equation of a tangent is in the form y is equal to mx plus c. The question now would be, what does m represent? What does m represent? M represents the gradient, right? And now, where does gradient come from? Gradient comes from your differentiation. It comes from dy dx. So that's how we relate a tangent to differentiation. Okay. So whatever gradient you get from dy dx belongs to the tangent. All right. Moving on, we are also going to talk about the normal. The normal, that's another line that we have to talk about. The normal. Right. So with the normal now, we are saying it's a straight line, right? But it is perpendicular to the tangent. Straight line perpendicular to the tangent. So if it's perpendicular to the tangent, what is it that we know about perpendicular lines? Okay. I'll put my equation of the normal. My equation of the normal, let's say y is equal to, let me call that m2x plus c, so that I will differentiate that from the m that is being used by the tangent. So for perpendicular lines, what we should always know is if you multiply their gradients, they should always give you a -1 if you multiply the gradients of the normal. So of the normal in the tangent. So in our case now, we had highlighted that dy dx was the gradient for the tangent. So that would imply the gradient of the normal would be equal to negative dx dy. Right. Why is it like this? Remember, these two gradients are supposed to multiply and give us a -1, like that. So that's the tangent, that's the normal. Then, of course, there's a little bit of something that we have to discuss before we jump into some serious questions there. Right, we have to talk about tangents or normals. Let's talk about tangent. Tangent first, being parallel to the x-axis. So if a tangent is said to be parallel to the x-axis, what does that imply? It means its gradient is equal to 0, which also implies if your dy dx is a fraction, right? A fraction whereby we have a numerator, a denominator, then in short, we could say the numerator should be equated to 0. Then let us also talk of the tangent. This time it's being parallel to the y-axis, meaning it's sharing the same gradient with the vertical y-axis. So now, what does that imply for the gradient? The gradient is equal to infinity because the y-axis is a vertical line, and of course, if in the case that probably your dy dx is in fractional form, numerator over denominator, then that could imply your denominator is equivalent to 0, so that it can be equated to infinity. So those are the basics. Now it's time to jump onto some questions.